The most revealing number in AI infrastructure may not be a chip count. In February 2025, Google said it had deployed more than 100 million lithium-ion cells across battery packs in its global data center fleet. Those cells are not there to run an AI campus for days. Their first job is more immediate: keep digital equipment alive through a power disturbance, while the rest of the backup system reacts. That distinction exposes a hidden bill. You are not buying one giant battery. You are buying cells, chargers, power electronics, monitoring, redundancy, safety engineering, testing, replacement plans, and operating rules. Some systems sit beside the building, others live inside the rack, and even when they never handle a real outage, they can still consume power and require maintenance. So the useful question is not, how much battery does AI need? It is, what reliability promise is this battery system being paid to keep? Start with the sequence. Utility power reaches switchgear, conversion equipment, distribution units, and finally the servers. If the grid drops, the uninterruptible power supply must react before the computing load notices. A 2026 Open Compute specification says a rack battery backup shelf should take over within 2 milliseconds after its trigger. Another Open Compute rack design calls for 45 to 90 seconds of battery holdup at full load. A much smaller NREL data center used a central UPS designed for 15 minutes, long enough for its emergency generator to come on. These are different architectures, not conflicting answers. The runtime depends on what must start next, how much load is protected, and where storage sits in the power path. This is why battery capacity alone is a weak purchasing metric. The design also has to specify response time, protected load, power quality, handoff logic, and the failure mode if any link between the cell and the server does not respond. AI changes the scale and behavior of the load, but it does not create one standard battery recipe. Berkeley Labs' 2026 reference case estimates U.S. data centers could use 649 terawatt-hours in 2030, or about 11.8% of U.S. electricity, with a wide uncertainty range. More infrastructure moving through the critical power path makes every percentage point of loss, every redundant module, and every maintenance decision more consequential. Pacific Northwest National Laboratory now models several storage layers for large data centers: low-voltage DC storage inside a UPS, rack-level battery backup, rack-level capacitors, and utility-scale storage. Each solves a different timing problem. A rack battery may bridge seconds or minutes. A site battery may support the grid or smooth a larger disturbance. A generator may carry a long outage. Treating all three as interchangeable hides both cost and risk. The bill grows from the service level the operator promises, not from an abstract number of megawatt-hours. Open a modern rack battery module and the cost stack becomes visible. The Open Rack specification describes a battery pack, a battery management system, a charger and discharger, communications, health monitoring, and other functional blocks. The shelf holds 6 modules in a 5+1 redundant arrangement. That spare unit is not wasted inventory. It is the price of surviving one module failure without losing the protected load. Move from the rack to a central or site-level system, and the surrounding equipment expands. Rectifiers, inverters, busbars, breakers, switchgear, controls, ventilation, detection, suppression, enclosures, and commissioning tests. Lithium-ion also adds a safety design obligation. Google says its battery backup designs undergo thermal runaway testing, while UL explains that large storage installations require fire propagation evaluation and site-specific protection. The cell is the most visible object, but the budget is really buying a controlled electrical and fire safety system around it. Reliability can increase capital cost and quietly reduce efficiency at the same time. The Department of Energy notes that a large UPS paired with an identical 100% redundant unit can operate at no more than 50% load, even at full build-out. Lightly loaded UPS equipment is often less efficient. Modular design changes that trade-off. Smaller units can be added as the data hall fills, keeping utilization higher and delaying some day-one spending. Google makes the same architectural point from the rack side. Its distributed battery backup scales with deployment, reduces the failure domain to one rack, and removes intermediate conversion steps between the battery and the machine. None of that makes redundancy free. It changes where the spare capacity sits, how fast it can be replaced, and how many failure domains one event can reach. The hidden bill is therefore architectural. Buyers pay for spare modules, spare paths, and enough operational discipline to prove those spares will work when the active path does not. A backup battery spends most of its life waiting, but waiting is not the same as doing nothing. The open rack specification says a module in standby remains fully charged, monitors the bus and reports status upstream. It caps standby consumption, including fan power, below 15 watts per module. It also calls for a forced state of health test every 90 days to determine end-of-life status. Multiply monitoring, periodic charging, testing, firmware, alarms, inspections, and eventual replacement across a large fleet, and the operating bill becomes continuous. The Pacific Northwest report adds another boundary. UPS batteries sized for tens of minutes can wear out quickly if they are used for continuous load smoothing. A battery warranty, therefore, is also an operating rulebook. Depth of discharge, temperature, charge windows, cycle count, and reserve margin determine what the asset is allowed to do. If a proposal counts grid revenue but ignores faster aging or reduced emergency reserve, it is counting the same battery twice. The battery may discharge rarely, but the UPS power path can operate every hour. That is where a small efficiency gap turns into a persistent bill. The Department of Energy gives a bounded example: a 15,000 square foot data center with IT. Equipment operating at 100 watts per square foot uses 13,140 megawatt-hours per year for the IT load. Raising UPS efficiency from 90 to 95% would reduce the annual energy bill by roughly $90,000 at 12 cents per kilowatt-hour, while also cutting cooling demand. This is an illustration, not a forecast for an AI campus. Its value is the mechanism. Conversion loss becomes electricity expense, then becomes additional heat that the cooling system must remove. A buyer comparing batteries without comparing the complete conversion path can choose a lower sticker price and still accept a higher lifetime bill. Efficiency needs to be measured at the actual loading range, not only at a favorable nameplate point. Now separate two assets that headlines often merge. A UPS battery protects the computing load. Its priorities are immediate response, power quality, and guaranteed reserve. A site battery energy storage system may have a broader job: grid support, load shaping, renewable integration, or longer ride-through. Pacific Northwest researchers warn that existing UPS batteries are not automatically suitable for continuous smoothing. Cycling can consume useful life, and some grid disturbances may force the UPS rectifier offline to isolate the protected load. That can create a need for a separate utility-scale battery or power electronics device. The practical lesson is simple. Megawatts measure power. Megawatt-hours measure duration. Neither number tells you which bus the battery connects to, what controller has authority, or whether the IT load remains protected during a grid event. Before valuing a battery, trace the one-line diagram. The electrical location can matter as much as the chemistry. There is real upside when the contracts and controls allow it. Microsoft says the lithium-ion batteries in its Dublin data center UPS were certified, tested, and approved for grid connection. Through an aggregator in Ireland's grid services market, the system can reduce the site's grid draw while preserving the UPS function. Google has also installed and tested a battery-based backup system at its St. Ghislain data center in Belgium, with the aim of supporting the local grid when backup power is not needed. These projects show that an idle reliability asset can sometimes earn a second job, but sometimes is the important word. The revenue case depends on interconnection approval, market rules, communications, warranty limits, state of charge, and a hard reserve for the primary reliability mission. Grid service is not free money attached to every battery. It is a separate operating contract layered onto a system whose first obligation is still to keep the data center online. To audit the hidden battery bill, ask 10 questions. What load is actually protected? How fast must storage respond? How long must it hold? What starts next? Where is the battery connected? What redundancy remains after one failure? What efficiency is expected at the real load? How are health, temperature, and state of charge tested? Who pays for replacement and fire safety compliance? And can grid service ever reduce emergency reserve? Those questions turn a generic battery quote into a reliability model. They also explain why two AI campuses with the same IT megawatts can carry very different battery costs. One may centralize UPS capacity. Another may distribute backup inside every rack. A third may add a separate grid-scale system. The visible cells are only the beginning. The real asset is the tested chain from cell to server, backed by maintenance, safety, and contractual limits. That is the hidden battery bill behind AI data centers.